Okay, so for this video, I'm just going to give you a little bit more detail on the equipotential lines and some unit conversion. First thing is, equipotential line, as I mentioned in the other video, it's a line with the potential is the same. So if I have my charge and I was to have the equipotential lines, you will see these rings around it. I showed you it before, we did this in the simulation as well. And you had a position here, anywhere along this line, the V is the same, maybe 10 volts. It is the same, same, all the way around. If this was a positive charge, and that means the closer I get, it will increase, right? So maybe 15 volts here. Everywhere here is the same. And maybe this is 20 volts. And everything around this line is the same, 20 volts, okay? So if you're moving along the same line, not in between, but along the same line, no work is done. V final minus V initial, 10 minus 10, 0. 15 minus 15, 0. 20 minus 20, 0. The only time there will be work done is if you move between the lines, because I am increasing my potential. Yeah, so it'll be 15 minus 10, this will be 5, and I'm gained 5 volts as I get closer. I will lose it as I get further away. Okay, so we'll convert from joules to electron volts, understand equipotential surfaces in more detail, and of course we've done the IG questions previously. So the electron volts just makes things a lot easier, because if you know the charge of an electron is times 10 to the minus 19, and then you have all these small numbers, which kind of makes it hard for you to compare different sizes and different values. So we can say that 1 electron volt is the energy that 1 electron will have when you accelerate through 1 volt of potential difference. Take 1 electron and you pass it through 1 volt, that's the energy. Of course, you will take you can do the work done, W equals QV, you can say Q 1.6 times 10 to the minus 19 multiplied by 1, you will get 1.6 times 10 to the minus 19 joules. Amazing. We call all of this 1 electron volt. W equals QV, yeah? Charge times voltage of 1, which will just be the same value as the charge. We call this 1. So if I want to double it, if I have 2 electron volts, it'll be double this. That's what you'll get. 4 electron volts, you will multiply by this number. And if you want to go the other way around, if you have this, you will simply divide by 1.6 times 10 to the minus 19. You will get electron volts. So this is how we will do it, and these numbers are a lot easier to use. So if you ever see EV, that's it. You can just multiply by 1.6 times 10 to the minus 19 to figure out what the energy is in joules. Okay, back to the potential lines. The equipotential surfaces. I've already shown you this. Becomes 0 all the way around. Very nice. This is what it's going to look like if you see the simulation, which I did actually show you. Okay, so it helps show us what the field looks like, and it points in the direction of decreasing potential from plus to minus. So here is a positive charge. You see positive, these circles are all equipotential lines. So if I choose this circle, this line here, go anywhere around here, this potential stays the same. It's a badly drawn outline, but you understand what I mean. This circle, and maybe the next one, or the next one, those voltages are the same all the way around. Further out I go, the more there'll be a change, okay? And it doesn't need to be like a big gap here. I can draw more if I want. I can draw less, I can draw more, it doesn't matter how many. This depends how many times you click the button in the simulation. So I must have clicked very fast and then not clicked and then clicked again at the end over here. That's what I did. So there are electric field lines going all the way around, as many as you want, okay? Negative charges will be the same. In the positive charge, we know it comes out like this. The field lines are coming out. That is very nice. And have you noticed that this is perpendicular? This is perpendicular. So that is something that can come up in a question, okay? The field lines are perpendicular. If I do little lines, you can see it looking like this. Again, there'll be as many as you want. I started drawing them, and then of course I must have stopped at some point. And this is going outwards because it's positive, and each line is perpendicular, as you can see. And if you have a dipole, which is 2 charges together, a positive and a negative, you have the equipotential lines, and right here, this straight line here is a 0. This eventually will curve around and come back to here again. That's what it will do. Oh, back to here again. It will curve all the way around. But as this point, it looks pretty straight. That is the 0, so I can call it 0 volts in between these two. Very nice. And if you want to look at the close-up, this is what it looks like. There's a field coming out, going in. You can see it going towards the negative side. And it ends up looking very equipotential. If the two like charges, it looks a bit like goggles. You have them here, and you have the field line, and it is always going to be like this, because it'll never reach 0 in the middle, so it'll never get to 0, and you will have the equipotential lines going like this. Very nice, because it loses some from this side, and it will gain some from this side, so it will just keep going in a straight line. Same thing can be said for a negative as well. It's exactly the same. Field lines look like this for a negative. This is a negative one example. Very nice, easy.